we're starting with set notation. We're doing 2 lessons of set notation, and then we're moving into Venn diagrams. And Venn diagrams use a lot of the set notation. So if you know it, it's a lot easier. Okay? So today it'll be a lot of this is what this is, and you've never seen it before, but it's not hard. So in mathematics, a set can be defined as a collection of distinct objects. For example, the number of on the faces of a die form a set. So the set of the faces on a die would be 1, 2, 3, 4, 5, 6, right? That would be the different set. Sets are notated by denoted, oh my goodness, denoted, thank you, by capital letters or by a description inside curly brackets. So these little squiggle symbols, these little squiggly brackets, mean the set of, okay? If your squiggle looks more like a random S, I don't care. Attempt a squiggle, okay? The more you practice, the better you'll get at the squiggle. An object in a set is referred to as an element. So the number 5 is an element on the number of the numbers on a die, right? How many elements are there on a 6-sided die? Well, there would be 1, 2, 3, 4, 5, 6. How many elements is that? 6. Okay. If I asked you for the number of elements, each one of those is an element, and it would be 6. So you can list the elements as a set. You can have a description of set in words, so like this, or you have it as a notation. But both of these forms here, I always turn into that form because you want to be able to see all the different numbers, right? It's a lot easier when you're comparing sets together. So the curly brackets, or the squiggles, together is read as the set of. The straight line represents such that. And E is a member of or element of. And it will just be part of your vocabulary as we go along. So at the beginning, it might be brand new, but by the end, you all know what they mean. Okay, so no worries. So we have the number of elements in the set is written as little n of A. So what I could have done here is this is A, correct? But little n of A would be actually 6. That doesn't mean that 6 is the only element in it. That means there's 1, 2, 3, 4, 5, 6 elements. Okay? So often they don't use the little n. They'll say the number of elements in A is. Why would they do that? Why would they ask you for the number of elements in something? Think about the method of question that you're asked on the diploma. Multiple choice and numeric response. Why would they ask you for the number of elements? It lends you to what kind of question? An answer to a numeric? Could I fill 1, 2, 3, 4, 5, and 6 into a numeric response box? No, you have 4 numbers you can fill into a numeric response box. Could you fill 6 into a numeric response box? Yes. So they ask for the number of elements in a set because then it can be asked as a numeric response question. If they don't ask you for the number of elements in that set, can you list 10 in 4 boxes? No. Can you write the number 10? Yes. Okay, that's why they do it. Note that the number 2 belongs to set A, but the number 8 does not belong to it. So you would say 2 is an element of A. Wow, this is messy. And then this would mean 8 is not an element of A. The order of listing the elements does not matter. So if you had the set of whatever is 1, 2, or it's 2, 1, that just means that it has the numbers 1 and 2 in it, correct? Or 2 and 1 in it. Does that change it? No. I always ask for your own welfare and for my welfare that you go from low to high, because then there's a good chance you won't miss one as you go along. And you'll see why I say that. Because what we're going to do is we're going to compare 2 sets together and see what is in both sets or what's in either or set, correct? And if you have them all in random numbers, you might miss one that matches the same in each set, right? Whereas if you do them always from low to high, you'll be able to match them a lot easier. Make sense? Okay. So we have consider class example 1. So we're considering the following two sets. The first set is P, and it's the whole numbers less than or equal to 3. So what you're going to do is on the back of that booklet, you have a blank page, correct? Oh, you don't. I lied. Oh, that's sad. On the front of the booklet at the very top, you have a blank spot. We agree? Okay. Right there, what you're going to write is some definitions, okay, to help you. So we did these in grade 10. You're going to go over them because if you don't know what they are, these questions are hard. So for example, natural numbers. If you don't want to put this at the top of the booklet, get out a different piece of paper and write it there. I do not care where you put it as long as you have it. So the natural numbers, I always say, are the natural ones that a little kid starts counting. So the natural numbers are like when my 1-year-old or 2-year-old started counting, what number did they start with? 1, and then they went 2, 3, 4. There was no 1-year-old. There might be, don't bite me, don't go Googling it. There might be a 1-year-old who goes 0, 1, 2, but probably not. And there might be a 1-year-old who's like -6, -5, good, great for that one. But we're going to go with the most common 1-year-old. And they naturally start at 1, 2, 3, and then they go till whatever they get to, which might be 3, that's fine. But they keep going, okay? It's the natural ones you count from when you're little. We agree? And we need to know these definitions because they'll say the natural number is less than 20. And if you don't know what natural numbers are, you know it's less than 20, but you don't know where to stop, right? So you need to know your definitions. So natural numbers are 1, 2, 3, etc. Then the next set is whole numbers. Does anyone know the difference between natural and whole numbers? Whole numbers have the number with a whole, which is 0, and then the exact same thing. Only difference is they have 0. Okay? Only difference. So we're little and we realized, hey, there's a 0 in the world. Then we got older and we got into junior high and they started telling us there's negatives and life started getting a little more rough. So they're called integers. The great thing about integers is still no decimals, right? So it would be ... start from negative infinity, -3, -2, -1, 0, 1, 2, 3, and onward. Okay. The other things we have are rational. Rational numbers could be fractions. If you can turn it to a fraction, it's a rational number, that's for sure. But fractions are rationals. And the reason why you can turn them into fractions, rationals, is because they're repeating decimals, and repeating decimals can turn into fractions. Okay. Either repeating decimals or terminating decimals. And terminating decimals are decimals that stop, right? So if the decimal repeats or the decimal stops, then we can turn it into a fraction, and then it's rational. We agree? Irrational are the ones that are irrational. So they're the non-repeating, non-terminating. They just go on forever, like pi, 1.3479, and forever. They just irrationally keep going. So non-repeating, non-terminating decimals. And what number system encompasses all of these? Do you remember? Starts with an R, rhymes with feel. Real, yes. So the real number system are all of these. So like I said, you can write on a separate sheet of paper, you can write it in the booklet, wherever you want it. But like I said, if you don't know what these are, the next question that we were going to do is hard, right? because you don't know where to stop. Okay. So P are the whole numbers. What does whole numbers mean? 0, 1, 2, 3, 4, blah, 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 right? The whole numbers less than or equal to 3. This is great, the wording, but I want it written as the elements because that will help me. So I start at 0 and then 1, 2. Do I include 3? Why? Because it says equal to. If it just said less than 3, I'd be done, right? Go back here for a second. N of P. N of P represents the number of elements in P. And on the diploma, they often say the number of elements in P. But if they did use a little n, now you'd see why, right? So the number of elements in P, how many of them are there? 4. You are correct. The next one says even whole numbers less than 10. What are the even whole numbers less than 10? We'll start. Do I include 10? Because it says less than. How many are there? 5. Often people don't know, is a whole number even or is a whole number just, or 0, is 0 an even number or what is it? So often they'll say the natural number is less than 10, not making that issue not even a problem, right? Don't even have to think about it because the natural numbers start at 1. So we wouldn't even have to think about 0. So that's what they often do. So we have 5. So NQ is 5. Okay? If we wanted to do this in another form, we could go P are the whole numbers less than 3. So if we wanted to do it, we could do X such that X is less than or equal to 3. I won't make you do it in this form. I just want to show it to you just in case you were given it. Okay? So less than or equal to 3, and then X is an element of the whole numbers, which is a W. So what you're doing this for is you're saying the variable I'm using is X, such that it's the straight line. X has to be less than or equal to 3. And of those X's that are less than or equal to 3, they have to be whole numbers. That's why you write it like that. Which one would be, which one could we use for Q? Well, Q, we would do X such that X is less than 10. We don't have an equal sign, right? And X is an element of the whole numbers. So we could use that one, right? Okay. Often it's in words. I rarely see it like this. It's in words or it's actually the elements are listed for you. But can you see if you don't know what a whole number is or a natural number, it could be a bit of an issue? Bless you. So this is where we're going to use our terminology. So Betty is defining sets using non-negative single-digit numbers. And I'm going to use, just for ease, single-digit natural numbers. So what am I starting at? 1. And they have to be single digits, so where do I stop at? 9. So E represents the even numbers. Okay? So the even single-digit numbers, natural numbers, would be 2, 4, 6, 8, and I'd have to stop because 10 is a double digit. not a single digit. Whole numbers, we're going to go natural numbers. Change that to natural. Natural numbers less than 7. What are the natural numbers less than 7? All of the natural numbers less than 7. Is that what you said? Sorry, I thought you went like 1, 3, 5. I was like, yeah, you're correct. I didn't hear you. 1, 2, 3, 4, 5, 6, and not including 7 because less than. I need to get my ears cleaned out as well as largened, enlargened, or with poor English, largened. Something. Nope, just want to use largened. I corrected it in the middle and said enlarged, but I'm just doing largened. Oh, these largened ears of mine. Odd numbers less than 7. Where do we start at? 1, 3, 5. Now, why are we starting at 1? We're starting at 1 because of this. The universal set. Okay? Within the context of any problem in set theory, there generally is some largest set that we have in mind. We refer to this as the universal set. The universal set is the set that we can only use for all of our subsets, for all of our little sets that are contained within it. Okay? So, what would the universal set be of this one? It's often in the question. So it says, Betty is defining sets using non-negative single-digit natural numbers. So from E, L, and O, what did I choose from? Non-negative, single-digit, natural numbers, right? All of these sets were pulled from that, were they not? That's the universal set that we could choose from. That's what the universal set is. So the universal set is non-negative, which I didn't need to write after, because the moment I put that it was natural, what is it? Non-negative. So we're kind of really doubling up here, but that's okay. Non-negative, single digit. And the reason why I threw natural in there is because I wanted to get rid of the 0. I didn't want to deal with it. So the universal set is the set that you choose all your little subsets from. Okay? That's your universal set. Very important. No, because I said natural. It would have included 0 if I didn't. So really, we don't need this because I put natural in there, right? Because once I put natural, they're not negative. So we kind of just doubled up on the non-negative part, just in case you missed it. Okay, subsets are important. Subsets get asked all the time. So I need you guys to understand what the heck a subset is. It's not a hard concept, but it takes a bit to remember what it is. Subset is represented by this symbol. What's great about that is it's just like a sideways U or a really long C. Now, what's great about it is you don't need to memorize that that's what the symbol is. They give it to you. They go, hey, look, this sideways U is subset. This is your formula sheet. This is the exact formula sheet minus the borders. You get this exact same one, all in the same order. Okay? So when you see your formula sheet, it looks exactly like this, minus the border. Okay? So you're given this. The symbol is subset. So say you forget what that symbol means. Go to your formula sheet and look what it says. Okay? Say you forget what subset is. Well, maybe you look and see the symbol and you're like, oh, I remember what that symbol was for. Right? So go to your formula sheet and look. What this means, a subset of a set is the set that contains some or all possible or possibly none of the elements from a previously defined set. All sets we deal with in a problem must be subsets of the universal set. Okay, what does that mean? All that means is if I say E, because we have a set E, right? E are the even numbers. So say I say E is a subset of U. In order for that to be true, everything in E must be in U. Everything in E must be in U. So this set, everything in E, must be in U. Is it? E contains 2, 4, 6, 8. U contains 1, 2, 3, 4, 5, 6, 7, 8, 9. Correct? Is every element in E in U? Yes. Can we have more elements? Sure, in U. But we have to have, at the very minimum, all of these elements have to be in here. Now, could I say E is a subset of E? Is everything in E and E? Yeah, they're the exact same. So that's why I said some or all could be in it. So every subset is a subset of itself because everything in E is in it. Okay. Is E a subset of O? E has 2, 4, 6, and 8. O has 1, 3, 5. Is 2, 4, 6, and 8 in 1, 3, 5? No. So E is not a subset of O. What if 3 of the 4 elements in E were in O? Would that work? If 3 of the 4 elements in E were contained in here? No. All of these have to be contained in here, or it's not a subset. Okay. What other one, which of the 2 up there are actually a subset of each other? E is not a subset of O. We've said that already. O is not a subset of E because 1, 3, 5 is not in 2, 4, 6, 8. L and O, but which way would we write it? Is O a subset of L or is L a subset of O? O is a subset of L because everything in O is an L. O has 1, 3, 5 and it is an L. Is L a subset of O then because O is a subset of L? No. L has 1, 2, 3, 4, 5. O doesn't even have enough elements to have all of those in it. So this for sure is not true. Do you understand subset? Very important. Really easy to do, actually. Really easy to forget about. Does everyone get it? Everything in the first one has to be into the second one in order for it to be a subset. Empty set. An empty set is a set that contains no elements. So in the set, you have no elements. It is empty. It even shows it here. 0 slash through it. No elements in an empty set. Okay? We will come back to empty set because it makes more sense when we do ands and ors, which we're not doing yet. Okay? So empty set just is a set that contains no elements in it. So are E, L, or O empty sets? No. E has how many elements? 4. So N of E, number of elements in E, would be 4. Number of elements in L, 6. Number of elements in O, 3. So they're not empty, they have elements in them. So you could either write it like this, or you could write it like this, a set with nothing in it. It means the same thing, there's no elements in it. Okay? Then we have the complement of a set. The complement of set A is the set of elements in the universal set that are not in set A. So the complement of the set shows it here. So complement of A complement is this little prime symbol, okay? So if I did the complement of E, E has what in it? What did E have in it? 2, 4, 6, 8. In order to give the complement of it, I also need the universal set. You need the universal set and that element in order to get the complement of it. So our E is 2, 4, 6, 8. Our universal set is what? What numbers were we allowed to look at? So what do we start at? 1, 2, 3, 4, 5, 6, 7, 8, 9. So our universal set is 1, 2, 3, 4, 5, 6, 7, 8, 9. E has 2, 4, 6, and 8. The complement of something is the complete opposite of it. Okay? So if E has 2, 4, 6, and 8, the complement of E will have everything but 2, 4, 6, and 8. So that's why we need the universal set, or we actually don't know what the complement is. Okay? So the complement of E complement of E, is everything but 2, 4, 6, and 8. Do you agree? So it's going to be 1, 3, 5, 7, 9. Does that make sense? E is the even numbers, so the complement of E ends up actually being the odd numbers. Exactly. We're going to come back to this in a few seconds. All right. So this next one is a totally different question, right? It's not based on anything that we looked at before, the single digit, all that stuff's gone. Whole new question, okay? This one has natural numbers less than 20 that are divisible by 3, and then natural numbers less than 20 that are divisible by 5. What does divisible mean? You can divide evenly, and you don't get what when you divide? Yes, the decimal. Explain why the set of natural numbers less than 20 is a suitable universal set. Why are the natural numbers less than 20 a suitable universal set? Remember, the universal set is a set of numbers that you look at that you can only take numbers from for your sets. What do both of the sets have in common? Natural numbers less than 20. So in both sets, the only numbers I can look at are natural numbers less than 20. That's why it's a suitable universal set, because in both those sets, the only numbers I can look at are the natural numbers less than 20. Okay? So now we have to list the elements, in A. So I want to first list the universal set, because look what I see. I see a complement coming up. And the only way I can list a complement properly is if I know all the numbers in the universal set, because once I have A, I just put every other number that's not in A into the complement. So it's way easier if you actually have the universal set listed. And I know it takes a bit to list them all, but at least you won't miss any then. So natural numbers start at what? Less than 20, we end at? Okay. And now you may be complaining that took you a while. However, how much time do you spend on Snapchat? So much. So you spend way more on Snapchat, too much than that took to write that. This will get you a good mark. Snapchat will get you a picture of a roof or your shoe or someone else's shoe for that matter. So this is better. Don't complain. It really didn't take you that much time. Okay? A. Natural numbers less than 20 that are divisible by 3. So which of these numbers, if I divide them by 3, do not give me a decimal? Starts at 3. I'm going to, instead of going right to B, I'm going to go to the complement of A. Is the complement of A easy to write now once we have the universal set and A? Yeah? It's just everything that's in the universal set that's not an A. Once again, don't complain. This doesn't take that much of your life up. Okay, so 1, 2, not 3, 4, 5, not 6, 7, 8, not 9, 10, 11, not 12, 13, 14, not 15, 16, 17, not 18, and 19. You agree? B is even way better. B complement is not better. B is way better because B is what's divisible by 5. So which of those numbers in the universal set, when I divide by 5, I don't get a decimal? 5, 10, 15. Why did I say the complement would be worse? You should write everything but 5, 10, and 15. But we won't, so it's okay. We're going to look at set C here for a second. Set C are the natural numbers less than 20, so same universal set, correct? But are multiples of 6. What are multiples of 6? Multiples of anything, you start with that number and then go up by that number. So C has the numbers 6, and then 12, and then 18, and then we're done. So little n of C would actually have 3, right? Or if I said the number of elements in C, you would tell me 3, because it's the way I could ask it. This one I could never ask it as a numeric response. Why? right? It would get you 5 digits, and I have how many boxes? 4. Okay, so I'd either have to change it up so the numbers were smaller, I had more single digits or something like that. Okay, let's answer these questions. You're going to tell me if they're true or false. C is a subset of A. What does that mean? That means everything in C, every element in C, every single one, not 5 out of 6. C has 3. Not 2 out of 3, not 1 out of 3, but 3 out of 3 are in A, correct? So C has 6. Does A have 6? Yes. Woohoo. C has 12. Does A have 12? Yes. Yay. C has 18. Does A have 18? Yes. So is C a subset of A? Yes. This is true. Can A have more? Can A have extra elements? Absolutely. But at minimum, it has to have C in it. Okay? C is not a subset of B. Is this true or false? Is everything in C in B? Well, let's check it out. C is 6. Does B have 6 in it? No, we're done. Okay, true. They want us to say the complement of A is a subset of the complement of C. What's the best way to compare them? Actually have those elements listed, correct? We already have the complement of A, but what don't we have? So I'm going to put here. Complement of C. And some people are like, well, I can just visualize it. That's great. You might miss one or two. So don't visualize it. You've used your time up on crazier things like Snapchat, like I said to you, or Instagram. How much Instagram time do you use, right? Netflix. You can write out not see. Yeah, a little bit more than we need. Okay. So C is everything but 6, 12, 18. So we have 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, and 19. So we have to check. Is everything in not A in not C? Well, it looks good so far because C has more. That's a positive. But we actually have to check. So A has 1 because everything in A has to be into this one. A has 1, C has 1. A has 2, C has 2. A has 4, C has 4. A has 5, C has 5. A has 7, C has 7. A has 8, 8, 10, 10, 11, 11, 13, 13, 14, 14, 16, 16, 17, 17, 19, 19. Boom. They're all true. Your homework is to do numbers 1 to 7. And then we go on to intersection and union tomorrow. So we have to understand how to do number 1 and 7 really, really well. And then the intersection and union isn't as bad. Okay? We're going to do that tomorrow. And then we start Venn diagrams when you come back. It's not a long unit.